biology, I'm going to have some stochastic things. There will be a little bit of dynamical stuff towards the end, but no biology in this talk. But I think a number of you do use Monte Carlo methods in your work, or study Monte Carlo methods even, and hopefully the rest of you will find some use of all of this. And what I'll talk about is mostly joint work with Jonathan Goodman at Courant and my colleague Matthias Motzfeldt. And some of the newer stuff is joint work with also joint work with my student Andrew Beach. So just so we're on the same page, this was working a minute ago.
There seems to be something in the upper right-hand corner. Is it like?
That's nothing.
No. Okay, I'll just use the key. So
Nope.
Nope. Okay. Great. It will not work. There it goes. Okay, it's just slow for some reason. Okay. Technical issues. Sorry. Maybe we should have stuck with the browser. Does active?
That's all right.
Yeah.
It's still open.
It's still open. Maybe let's go back to the browser and see if that works better.
It's probably installing some
I would
updates.
say it's probably doing some massive update in the background.
Windows 10.
There it is, McAfee. Get that thing off of there, you'll be fine.
Windows 10.
You
This is
turned
the
the
live
Wi-Fi
Windows
on?
10.
Yes.
Sorry about
That was probably put on, that was probably some other Mac multi-level marketing.
It's not Mac. It's Windows.
that. This is Windows.
Elias. Don't blame the Mac.
Click sign one more time. I don't know.
Okay, great. Thank you so
Just
much.
like the lamp
Okay.
BBC sent you.
Yes, this is fine. Okay, great. Thank you. Sorry about that. Okay. So just so we're on the same page, I'm going to start with a very, very, very brief introduction to Monte Carlo methods.
Might be on the same page for a long time.
Oh,
Fair enough.
too easy.
So basically, Monte Carlo methods are just algorithms for generating samples on Fourier distributions. So you've got finite dimensional PDFs of some kind, some Fourier density, and you'd like to draw samples from it. Okay. And the main reason, not the only reason that you want to do this is you can estimate expectation values of observables. So if some function whose expectation value, some function phi whose expectation value is equal to the distribution p you like to estimate, once you have a lot of samples, you can just, by taking an average in the limit of large infinite number of samples, this will, under very general condition, converge to the integral, the expectation value. Okay, and the Monte Carlo methods have a lot of applications, as most of you know. They're often used in statistical mechanics, especially in equilibrium statistical mechanics, where you start with the distribution of some known form involving the Hamiltonian of the system. Okay, so you like to compute expectations, and usually these are very high-dimensional integrals, and so it's not possible to do numerical quadrature. And so Monte Carlo is often the only efficient way of computing these expectations. The thing that motivated a lot of the work that I've been doing is actually data assimilation and filtering. And so in these applications, which I'm actually not going to talk about in this talk, but although I have a slightly related example. The goal is basically you have a stream of observations coming in in the form of a time series. So for example, maybe temperature and pressure readings from various observation stations at different times, and you'd like to estimate the state of some physical system, so the local weather system, for example. Okay. And so sampling, it's often, these kinds of data assimilation problems are often approached in a Bayesian way, and so you treat the physical model as providing a prior, and then you try to condition on the data as they come in, and you try to draw samples from the posterior distribution. Okay, so heuristically, that's how a good number of data assimilation methods work. And so having efficient sampling methods is often very useful in these applications. And then more generally, in all sorts of different applications of Bayesian statistics, you have some kind of complicated posterior distribution that you like to draw samples from. Okay, so Monte Carlo methods have become very essential in those areas. And there are also lots of other applications that I have not mentioned, so to biological applications, for example. Okay. And the problem basically, so this talk is basically going to be a numerical analysis talk. So I'm going to focus in this talk on a couple of things that make Monte Carlo sampling hard in various situations. One is that you can get very easily very complicated distributions, okay, even in relatively low dimensional settings. And so I'm going to apply dynamicist. So I'm going to give you a dynamical systems example. So this is the very well-known Lorentz equations. System of three nonlinear ODEs coupled together. Everyone has seen this butterfly attractor. We get this chaotic behavior. So I want to ask the following question. So suppose the system started at time 0 with some unknown state. Okay, actually that's too early. And so I started somewhere in phase space, and then I observe the state of the system, maybe with a little bit of noise, at some later time, and I want to infer the initial condition from that observation. Okay, so this is kind of a baby version of the kind of problem people have to solve in data assimilation. So a Bayesian approach to this could look something like this. You start out with some prior distribution, and so it could be a Gaussian, maybe with some variance centered as some guess about the initial condition, and then you have some posterior, which is your estimate of the initial condition given the data, so the observation at the later time. Okay, and you can work out the arithmetic, work out the calculation very easily. You're going to get some distribution of the following form. E to the minus f, where f is a combination of two terms. One is, so this quadratic part just comes from the prior, okay, so that's just a Gaussian. And then because you're looking back at the past, the flow map phi t of the Lorentz equations very naturally appears. Okay. Now, the thing that's interesting about this is that x0 here is the variable of interest.
So your likelihood here is just the flow.
Yeah.
The deterministic flow.
The deterministic flow, yeah. Yeah, so no noise in the dynamics. There is just, do I even have a noise model for the observations? I guess there must be. Yeah. But anyway, the dynamics is deterministic. And so x0, the initial condition is the variable that you care about. Okay. And so the dependence of this distribution is actually through this very complicated flow map. If you so as t increases, this map becomes very complicated because it will map over balls to something that looks like that attractor. Okay, so it's an incredibly complicated map. Okay.
Is this a realistic example?
I'm sorry?
Is this a realistic example? Or just a complicated example?
It's a so it's not realistic in the sense that nobody who models the weather will actually use this because this model is not correct. On the other hand, this problem is not trivial to do. It's a good test problem.
But it is a truncation of a realistic model.
It's
Right.
it's an over truncation of
An over truncation, yes.
It's
But it
not
comes
You're
from-
trying, the way, do I understand right, you're trying to predict what the initial starting condition is
Yeah.
from the weather now? Usually we want to
from
do it
the
the other
state.
way around.
Well, so this looking back in time is technically known as a smoothing problem. So there are situations where you want to do this. Of course, usually you want to do forecasting also forward in time, and filtering, so predicting, estimating the present state. Okay, so all these problems do come up, and this is sort of this is a nice test problem because you can tune how hard it is by just changing how big t is, and if your method couldn't do this problem, you can do anything more realistic.
Kevin, I would normally expect this posterior to be a product of the prior and the likelihood. So
Yeah.
I see the prior, the likelihood looks
Yeah.
like it's that d minus
Yeah.
vt over.
Yeah, so this is just been Gaussian noise model.
Yeah.
It's not double, it's over epsilon, right?
No.
There should be, yeah, I think I'm assuming implicitly the variance of the prior and the noise are the same. Then you just get, yeah. But of course you can make them different. That's just a simplification. Okay, so this is kind of a toy problem, but it's not as trivial a toy problem as it may seem. And if your method really couldn't do this one, you couldn't do anything more realistic. Okay. Okay, so a second class of problems that I will talk about later on in the talk are what are well, actually, sort of a special case of what are called rare events. So here I'm thinking about a stochastic differential equation, and system of ODE subjective to flat noise, and I'm interested in maybe estimating the probability of some event whose probability of occurrence is small, in the precise sense that as epsilon goes to 0, it becomes very small, exponentially small. Okay. And so this is another kind of problem that you can study with Monte Carlo methods because you, so if you discretize, I see I've left out there's a bunch of typos here, sorry. There should have been xm plus delta t times f of xm. So this is meant to be the Euler truncation of the SDE. So if you discretize this problem, and for simplicity, let's think about the easiest case of this problem where the final time is fixed. Okay, then you just have again, you can estimate this as the expectation of some indicator function for the event. And so this is, again, a very high dimensional integral that you can try to estimate with the Monte Carlo method. Okay. And so these are so the methods that I'll be talking about, we think could be useful for problems of this type. Okay. And obviously, high dimensions always come up, so just mention that. But you can get very complicated distributions even in not very high dimensions. Okay. All right. So so the simplest kinds of Monte Carlo methods are ones that give you independent samples. So you give a PDF, a direct Monte Carlo method. This one that gives you IID samples from that distribution. Okay. And in low dimensions, so in 1 or 2 dimensions, there are reasonably effective general methods for doing this. But in higher dimensions, basically we have good direct Monte Carlo methods for special distributions, Gaussians, uniform distributions over simple domains, and so on. There's really no good general direct Monte Carlo for high dimensional problems, or for very complicated distributions even in 3 dimensions. And so usually you have to give up on something. So many of you are familiar with Markov chain Monte Carlo, so you give up on independent samples. MCMC methods give you correlated samples. And then another thing that you can do is to settle for weighted samples. So samples that really come from, since I'll explain, from the wrong distribution, but you compensate for them by attaching weights to the samples. Okay. And of course, there are also combinations of these ideas that people use. Okay, and so this talk, I'm mostly going to be focusing on weighted samples, also sometimes called importance sampling. Okay, so here's the outline. So I'm going to go over some relevant background, and then I'll talk about some. I'm actually really not going to go into the analysis of the algorithm so much, but just the results because the techniques are pretty standard. But they do give you some insights into these algorithms, so in particular, something that we call symmetrization, which is a general way for improving the worker of these, the performance of these sensors. And then I'll talk about some examples and then some ongoing work that we're trying to extend this to SDEs. Okay, so importance sampling. So the idea of importance sampling is that you want to try to, so you have some distribution that you want to try to sample from, P. It may be too complicated to sample from, but there may be a distribution that's sort of nearby that you know how to sample from. So I'm going to call that a proposal, and that's going to be doing like Q. Okay. So you can choose a proposal distribution Q to generate what I call weighted samples. By weighted samples, I mean that so there are pairs of random variables, x and w. So the x's live in your sample space, and w's are positive numbers. And they have the property that if you take properly normalized weighted averages, as n goes to infinity, they converge to the integral you want to estimate. Okay. And if that happens, then we'll call x and w the weighted samples from P. Okay. So keep in mind, if you just look at the x's alone, they will be samples from Q. So these weights are compensating for the fact that you're sampling from the wrong distribution. And we'll use this notation W to denote this wave function. And you can figure out very easily that the wave function has to be proportional to p over q. Okay, so it's the Radon-Nicolson derivative of p with respect to q.
So Kevin, remind me, this estimator is biased, right? Is it?
No.
No, it's not biased.
No, it's not biased. So the whole point of doing this is that if they're IID, you get unbiased estimates, but you change the variance. Okay. So let me give you an example. So suppose you want to calculate estimate the tail probability of a Gaussian. Okay. And so so there's a picture of a Gaussian, and that's the tail. Okay. So the direct Monte Carlo way of doing this is you might draw n samples from your standard Gaussian, and then you just count, right? So you apply the indicator function to your sample points. You just count how many land in that tail, okay? And if your A is more than, I don't know, 3 or 4, you're basically, all of a million samples going to get 0 in that tail, okay? Or maybe 5, I don't know, okay? But the point is that that area is very small, and so you can get very few samples in the tail. And the important sampling approach to this would be to sample instead of from the normal standard normal, you sample from a shifted normal. Okay, so just shift it so that the mean is centered at the cutoff. Okay. And then you can just count how many samples in that tail. But of course, you're sampling from the wrong distribution now, so you have to correct that. And the way to correct that is just attach a weight. And the weight is just going to be, in this case, the ratio of the PDFs. And so the fact that you have to attach these weights actually introduces additional variance into your estimator. But you're going to win by just having so many more samples in that tail. Overall, you're going to reduce the variance by astronomical amounts. Okay. And this example, even though it's very simple, also points out a very important thing, which is that so I get an unbiased estimator. I can lower the variance by choosing a good proposal. But I could also increase the variance by choosing a bad proposal. Okay? And so choosing a good proposal matters a lot in doing important sampling. And so most of this talk, I'll be focusing on a class of important samplers called implicit samplers. So this was introduced into the literature by Alexander Turin and collaborators a few years ago. There's also mirrors certain methods that I'll say a little bit more about for sampling rare events for SDEs that were introduced by Jonathan Weir and Van der Langden, and also Paul Dupree and Kostas Spiliopoulos and various other people. Okay. So implicit samplers are, in their most basic form, are designed for the following kind of problem. So suppose you have a PDF as your target distribution. These guys were interested in data assimilation problems, and so for various reasons that I won't go into right now, for their applications, you often get distributions that are unimodal, but not Gaussian. Okay. And so the way you say that it's unimodal is that so they assume their PDF has this form e to the minus f. F has a unique minimum at 0, and that and you might as well just normalize it to 0, and then that is positive for x non-0, and it grows sufficiently fast so that this thing is actually a PDF and have as many moments as I like. Okay. And the basic idea behind implicit samplers is actually really just trivial. This is the simplest thing you can think of, which is you want to pick a proposal that's as close to where this your target PDF is maximized as possible. Right? So that's the idea. And so more specifically, you want to pick something called a reference PDF, here denoted by pi. So for example, a standard normal in d dimensions. Doesn't have to be that, but that's a convenient one to use in many applications. And then we're going to find a mapping, okay, so one-to-one, so a bijection of your sample space onto itself and also differentiable, such that the f composed with this map gives you something that is that looks like c squared over 2. Okay, so this is part of the preference distribution. And the reason for where that comes from is that if you take the put minuses on both sides and exponentiate, what this is that e to the minus f, after you do this coordinate transformation, is approximately equal to your reference distribution. Okay. And the way you're going to use this is that you're going to use x of c as your proposal. So the idea is you're going to draw random samples from your reference distribution, and for Gaussian that's very easy to do. You're going to pipe it through this map, and then whatever distribution x of c has, that's your proposal. Okay. Now, of course, x of c is not going to have the target distribution e to the minus f, even if this equation is satisfied exactly, because when you do a change of variables on a PDF, there's a Jacobian that gets introduced. But the idea behind implicit samplers is that hopefully this is a good enough approximation, and that just introduces relatively little distortion. That's sort of the intuition. And no, Pete's not happy.
I'm just confused.
You're confused.
Let's keep going, it's fine.
Okay. If there are any questions, I'm happy to.
Is this,
Yeah.
is we doing this with sub-solutions? Remind me, is that what
With
it does?
sub-solutions,
You take the log of that and you put sub-solutions?
maybe, yeah. I don't know what he is doing with sub-solutions.
If you
Exactly.
take the log, this
Yeah.
solves the
But a lot-
Jacobi equation. It has a.
Yeah. So a lot of what
Then you put something over it.
Yeah, a lot of what Dupuy and Wang and Skiapoulos have done in the context of SDEs is sort of analogous. And there you solve an optimization problem, so you naturally get how much. Yeah. So this is sort of a finite dimensional kind of version of that. So hopefully with the examples, I'll be more clear. So implicit sampling is really just a general idea. There are lots of different specific realizations of these ideas. And so I want to mention two. One is something I'll call the linear map method, which is actually fairly well known, I think, even before certainly way before Shoren and these guys wrote their first papers. Okay. And the idea is very simple. So remember, we assume that f has a unique global minimum at 0. Okay. And so you basically just fit a Gaussian to the maximum of your target distribution. And so you find the minimum, you compute the Hessian, and then you factorize it somehow, and then your sample is just the Gaussian that matches the covariance structure implied by the Hessian of the target distribution at the maximum. Okay. And so basically, if your distribution looks like this, you just fit a Gaussian around the max. And then you can work out the weights. The weights are just they look like that. And then there's a second method that they introduced. They called it the random map method. It looks like it works like this. So first, I'm going to make a slight simplification in the notation. I'm going to assume that I've done all this, and I've changed variables so that the Hessian is equal to the identity. That just simplifies the notation. And then the way this random map method works is you draw your Gaussian sample C, and then you scale it with a scalar factor lambda, so that it satisfies this equation. And so what you're really doing is that you look at C, and then you look at the level set of the Gaussian center at 0 that it lies on, and you scale it until it hits the corresponding level curve of F. And so this is another way, so you can check. I'm sorry?
That was too quick to absorb.
Okay. Yeah. I'm going to tell you. Yeah.
So you're going to come back to that?
Yeah.
Okay, fine.
So what that's doing, so I rearranged this slice.
So the lambda, how do you pick the lambda?
So the lambda is picked so that you solve this equation.
Thanks.
Yeah.
Marcos is working for me.
Yeah. And the reason you want to do that is that ultimately goes back to this idea, is lets you satisfy this equation exactly. Okay. But with of course this equation, if you think about x as a solution of this set system of equations with c given, x is highly underdetermined, right? And so they're sort of and so they're picking a particular solution that comes and taking c and just scaling it. Okay. And there's always going to be a unique solution with a positive lambda if the level sets of F are basically star-shaped with respect to the origin.
Okay, so like a nonlinear variable. So I guess it's like instead of trying to take the L adapted to the H,
Yeah.
you're doing it this way instead. Is that right?
So you're doing both adapting the, you are doing this as a first step, doing basically that, but you're additionally doing.
Oh, I see,
You're doing a linear correction on top of it.
Yeah, right.
And the idea is that maybe this will capture more higher order stuff.
Right,
Okay. And if you do this, even though you're solving that equation exactly, it's still not going to give you exact samples because it's a Jacobian that comes from doing a linear change of variables. Okay. But the Jacobian actually turns out to be calculated with a little bit of work. There's a kind of ugly formula for it, but it's computable. Okay. And in terms of the gradient of f and various pieces of data that you actually would have already computed anyway. And so this is the random map method. Okay. So these are the two implicit sampling methods that I'll focus on. So I should say, just as a matter of practical implementation, both methods, in both methods, the most expensive part is actually the part that I assume at the beginning, which is given the distribution, you need to first find its global minimum, and then you need to find out what's there is. And so, so that's an expensive step. Okay. And so to justify that computational expense, it's really because you get much better samples from this kind of sampler. And both methods also need a Hessian, although if you found them, if you minimize f by some kind of derivative-based method, then you would already have the Hessian anyway. So that usually comes for free. Random map is additionally more expensive because for every sample you need to do a 1D nonlinear solve. Okay, so that's maybe a few iterations of Newton or something. And so so there's a little bit more overhead there. And okay, so before I move on, I hope that's sort of reasonably clear. Is there any questions? Scott's hearing this for the second time.
So lambda is a function of just the unit vector in x direction.
Yeah, you can also get that. We'll go ahead and write it.
No, I'm wrong.
Well, you can also look at the unit vector. You can also think of it that way. There's an equivalent formulation where you can think of it.
Yeah, it's fine.
Okay, so those are the two kinds of methods. So in order to talk about the results of the analysis, I need some work comparing the performance of important samplers. One very common way of comparing the performance of important samplers is by looking at the relative variance. So the variance of the weights divided by the mean square of the weights. And this is also, if you take q plus 1, it's easy to see that this is the second moment divided by the square of the first moment of the weights. And one intuition I can give for this, there are various ways to interpret this quantity. One interpretation that's often given is that you can think of n over r as a kind of effective number of samples. And so the bigger r is, the fewer effective number of samples you have, because the variance of the weights is going to introduce variance into your estimates. And so if you have independent exact samples, then q is 0. And if you have a really bad sampler, then q can be very, very big. Okay. And so this is the means by which I'll evaluate these samplers. Jonathan is following. So I should say
if exact samples, then
yeah.
Q is then R is 1.
Yeah.
Because it's the weights are the weights are 1.
Yeah.
So then it's right.
And I should say that this is just a rule of thumb. There
Yeah.
is actually no real. I dug through the literature and I've tried looking at this thing. There's no real good mathematical justification, but it's convenient because it lets you compare samplers without referring to
This
the
is Lou
observable.
and Harvard. Yeah.
I'm sorry. Yeah, this came from these guys at Harvard.
Yeah.
Okay. So okay. So assume for our test so for our analysis, we're going to assume the target distribution in this form, and then we also assume reference distribution that's a Gaussian. And the basic idea is simple. We're going to take this quantity Q and just expand everything in epsilon. Okay, so that's really the strategy. We do want to note that so one thing that what's sort of transparent is that as epsilon goes to 0, Q epsilon goes to 0. which is the nice property you have, which is saying that in the small noise limit, these samplers are good samplers. Not every sampler actually has this property, even though it may seem obvious that you want some property like this. Before I describe the analysis,
I'm sorry to interrupt, but you mean that
Yeah.
the small noise limit,
yeah,
you concentrate in the minimum anyhow, right?
yeah. I mean,
So
that's right. I mean, so by construction,
it's a naive,
yeah.
it's a naive comment, I'm saying.
No, but that's exactly what's happened here. Okay. So if I look at this limit, well, for one thing, it's tractable. It's one of the few situations where we can say something general. The original application when this comes up, where people were looking at particle filters for SDEs. For those of you who know what particle filters are, distributions of this kind very naturally arise, and you can think of the step size as a small parameter there. Okay. And then I'll discuss later why this analysis is relevant if you're interested in very dense SDEs with small noise. Okay, so what are the tools? So we're basically going to assume that f is as smooth as you like, and then we take a Taylor expansion. And the basic tool is just very standard Laplace asymptotics. For those of you who know what I mean by that, on finite dimensional distributions. If you don't, I'll tell you in a bit exactly what we do. And I just want to mention that the various things that come up are all Gaussian integrals. So if you really need to know coefficients, there's Brooks theorem and so on. We can really evaluate them. Okay. So in a little bit more detail. So Q is the variance divided by the expectation squared. Okay, and so in our problem, because we started with a Gaussian reference, everything's going to be a Gaussian integral. So for example, for the linear map, the wave function is this, and then so you can Taylor expand. Notice that when you choose a Gaussian as your proposal with covariance fitted to the given by the Hessian of the f at maximum. The effect of that is it cancels out the second order terms, so you only get all the higher order stuff here. And so the second moment is just some ugly integral like that, and the point is that it's a Gaussian integral, and so are all the other factors in this expression. So you can expand everything, and so if you just do formal and the Gaussian, because you have a Gaussian there, you can just do formal epsilon expansions, and everything can be justified, and you will get the results that we have. Okay. So the analysis is pretty straightforward, but it does yield some interesting.
So everything is a Gaussian because of the choices you've made, right?
That's a choice I made there.
In the very beginning.
That's right. So if you chose
Try
a
to be
different,
fancy, this thing.
if you try to be too fancy with the reference, then this analysis
might
won't work.
have to do something else.
So the reason the Gaussian reference is natural is for particle filters, because if you do SDEs with the word of discretization, then that transition density is sort of is a Gaussian. So that's really why they emphasize Gaussian so much. Okay, so for the linear map, so the results are useful for understanding these, or give you some insights into these methods. So for the linear map, you find Q epsilon is order epsilon, and then the remainder is the order epsilon to the 3/2. And the coefficient of the order epsilon term is the cubic terms squared, the expectation of the cubic terms. And for the random map, it's an uglier calculation, but in the end, it's still Gaussian integrals. Everything can be evaluated. And what you get is the following: it's still order epsilon. The coefficient has some dimension-dependent term. This pretty rapidly goes to 1 as b becomes large. Okay. And so basically, you have the same coefficients in these two methods. So which is kind of a surprise, because you look at the random map method, it really should be more accurate. But for small noise problems, it's really not. I'm sorry?
Because the whole correction is
Yeah.
how it deviates from being Gaussian.
Yeah.
So the fact it's the Gaussian.
That's right, exactly. Okay. So when you think about it for a moment, it's not surprising. Okay. Now, the interesting thing though is that the coefficients involve the third derivatives of your log likelihood at the maximum, and that's an interesting feature because there's a general principle in numerical analysis that whenever you can introduce some kind of symmetry into a problem, then you can cancel all odd order terms. So can we get rid of these order epsilon terms? Okay. And and it turns out you can. what you want to do is you, so for the linear map method, for example, the weights look like this. And what you want is you want some kind of symmetrized method so that the weights after symmetrization, however you do it, look like, well, they have to be P divided by the proposal. You want it to look like W plus W of minus X divided by 2. So we can get rid of those cubic terms. And you can do that in the following way. To simplify notation, I'm going to assume the Hessian is equal to identity again. So you sample from the Gaussian standard normal, and then you just compute the weights that you would get for the that you normally get, and also the weights attached to minus the proposal. And then you just draw one of the two with probability proportional to the weight, and you just can check you have all these properties. So that symmetrizes the samplers. And you can calculate the variance, so you can write down all from the proposal, and the variance is, so you can calculate the Q for the symmetrized linear map, and you get something like epsilon, so you get order epsilon square, and then more higher order terms, and then the coefficient is now a variance that involves fourth derivatives. And so now, so this is the best you can do by symmetrization, because you can get rid of fourth derivatives by symmetrizing. Okay. So it does give you a higher order as measured by Q. And you can do the same thing with the random map method. The algorithm is actually very similar. So you sample your reference Gaussian random variable, and then you let x plus and x minus be defined the following way. So so this is the formula, but the picture is more easier to explain. So you sample your C, and then so this is the level set of F you're trying to hit, and so lambda is the solution that you get by going forwards, and then minus lambda. So this thing, the reflected sample, the symmetric sample, is the one you get by going the other way. And then you output again one of the two with probability proportional to the weight. And then you can go through a similar analysis, and you find that essentially you get the same thing. So you get order epsilon square. I forgot to write down the remainder, but it's the same order. And then there's a dominant part of the coefficient is the same thing. And then there's some other constant that has explicit dependence on dimension. Yeah, okay. And so, so in terms of, yeah, so anyway, so you can increase the order of this. So how am I doing? Oh, okay. So I'm going to go back to this example that I showed at the beginning. So I have the Lorentz equations. I'm going to observe the, I should have written this on the first slide. I'm going to observe the state plus some small Gaussian noise. Okay, so what I'm trying to do is take the observation at later time and infer the initial condition. Okay, so this is a standard smoothing problem. And okay, and so all this I said before. So if you compute the Q, so one of the nice things about this problem is that you can tune how non-Gaussian the posterior distribution is by changing the observation time t. And then so if you look at Q as a function of t, you can see that the symmetrized random map beats the symmetrized linear map slightly, and then both are much better than the unsymmetrized version.
Just to get a time scale in my brain, what's the time step you're having to use here?
T here is
So H.
Oh, you mean the actual integration time
Yeah.
step? Oh,
I was just trying, because that gives me some idea of what 10 to the minus 2 is, right? And what's the
the
stiffness
time
of
step
the-
I don't remember.
Okay.
It's like I 10 to the minus 3 or something with the
Alright.
or 10 to the minus 2 with the Runge-Kutta. Yeah, I
So-
don't remember.
So the first ones are like one time step. and
Yeah.
The last
So
ones are
so
like,
this is not very far in time. One of the problems is that if you go too far in time, before the distribution, before it even starts to approach the Lorentz chapter, the posterior is going to become multimodal, and these methods, then you gotta do something special to handle multimodal distributions. You can also fix t to be some number, and then so this really t equals 0.05 is actually not that big, but this is just to check the scaling of Q goes like as the theory predicts. Okay, so you can see that. Okay. So in the remaining few minutes, I want to mention so some efforts that we're currently making to try to extend this to SDEs. Same typo because I just copy and pasted the formula from before. There should be well, no, so this is SDE, that's fine, but I'm going to have a discretization. So I have an SDE. I'm fixing the initial conditions, and then I'm going to change the problem slightly. I'm going to try to estimate expectations of the following spectral form, e to the minus g over epsilon. G is a function, scalar value function, evaluated at the final time. Okay? And condition on this fixed initial condition. Now, this may look like a very strange class of things to consider. This is motivated by thinking of a function of this form as approximating a indicator function. So you can think of g as being very, approaching plus infinity outside the set and then going to 0 in the set. So this is a softened version of the indicator function. And so you can discretize this problem. Here's the typo. So this should be xn plus. This expectation becomes an integral of the following form, where this capital F now is a function that lives on the discretized path space. And you can write it out. It looks like this. So there's a quadratic part coming from the fact that I chose to use a word of discretization, and so I've transitioned this. These are Gaussian, and then there's a final cost. So there's that g, which is the function I apply at the final time. Okay. And so this problem is slightly different from this Lorentz example. So earlier we had a distribution that's hard to sample from. Here we actually have a distribution that's relatively easy to sample from. So our distribution is just the distribution implicitly defined by this discretized SDE on the path space. But the expectation I want to compute this observable may only be appreciable on some set of small probability. Okay. And so even though my distribution is easy to sample from, I may not get very many samples that hit the support of this function. And this is so this is a little bit like a Gaussian tail example. And so our attempt number one, and I'll tell you why this is attempt number one. This is not. This only works sometimes. Is you try to extend the linear map to just directly sample from distributions to apply it to objects like this. Okay. And the idea is very simple. You just do exactly the same thing as before. You take now. You try to find the minimizer of this function condition on a fixed initial condition. So you have this function on some high dimensional space. Okay, so I'm going to call this maximum C1 to Cn. Okay, so and then so using an underline to denote this discrete time path, you can basically generate your samples as Gaussian perturbations of this most likely path, okay, where L has to match the covariance structure. And then the estimator is just what you would think of. It's basically the e to minus f divided by the distribution you sample from. So which is in this case a Gaussian. And then there has to be so you can figure out the normalization constants. The ratio of the normalization constants has to be included, and that's your estimator. And you can do this and. I guess I also want to mention you can also symmetrize this, and okay. So let me show you how this works on a toy example. This is the simplest example that sort of captures a lot of the problems with very advanced sampling, but also as you'll see in a minute, also tells you why this linear map method has certain defects. And so the example is this. You look at just Brownian motion started at the point that's not necessarily 0, and or the variance that's parameter that's not necessarily 1. Okay, so you have these scaled, shifted linear processes. Okay. And the thing that you want to compute is the expectation of e to the minus g for some g that looks like maybe like that. Okay. And so, so for this problem, you can apply the linear map method. So you go through all the steps, and it works fairly well. And you can also compute the Q, and it gives you the scaling that you expect in the theory. Okay. So, so that's kind of nice, except in most applications where you might want to do this, the F that you care about is going to be multimodal. Right? So linear map really depends on saying that there's one dominant mode that captures most, if not all of the kinds of behavior you want to see. But F can become multimodal very easily, either through the nonlinear parts of the dynamics, or because you pick a G that's not unimodal. Right? And so, now I don't like the way I arranged this. So I'm going to skip the algorithm and talk about the example. So for example, if in the Brownian motion example, if I simply change my observable to having 2 bumps instead of 1, okay, so that already is going to be a situation where the linear map won't work. But you can handle that with something that we call dynamic linear map, which works like this. So I'm going to first define a function f that depends on starting time n. So this is very, very much like what I had before, except you're starting at n instead of 0. And then what you do is just iterate. You basically you do the linear map from time n forward, and then you take one step of what the linear map says to do, and then you repeat. Okay, so you discard the rest of this optimal path and compute by just restart. And this is very, very similar. It's in fact a perturbation of something called the gradient simulation method that Ed and I were introduced.
This is like the kind of the committer function.
It's is it like the committer function? Is it? I told something saying. I don't know if it's like the committer function. Because that's the. It's more.
What's the set?
It's different.
Saying that you want to get that endpoint. You want to follow that path.
It's like I don't think it's got anything to do with the committer function. This is a different context. But we can discuss that later. This is like doing. Well, anyway, yeah, I don't know what it is.
Ignore me.
So this is basically the same as their method, actually. So they introduce a method that's very similar. The only thing that's different is we're actually making small corrections to the white noise part of the process, actually. Okay, and so for this 2-bump example, you can see the so this is my final slide. So for this, okay, this is not optimally arranged. Sorry to flip back and forth. So for this problem, there is a optimal distribution to sample from, and that's basically the PDF that's proportional to e to the minus f. Okay. If you look at marginal, at the final time, it's going to be some tilted version of these 2 bumps. And so this is the distribution you're trying to achieve. If you sample using a linear map and you look at the and build a weighted histogram out of that, when you get out of that algorithm, you would get something that's peaked only on one side. And that's because I'm starting off with the starting point that's to the right of center. It's going to pick one optimal path, which is to go to the closest maximum, and then just follow that, and then do small perturbations around it. So it's going to completely miss the fact that I can maybe go somewhere else. And then if you have a dynamic linear map, then the times when you do go left, you'll pick that peak, and then you go to where you pick the right peak. Okay. So that corrects for this efficiency. The thing that I don't have results to show, so that's basically the end. The thing I don't have results to show is that, and what we're hoping is that when you symmetrize this dynamic linear map method, you can actually get higher order behavior. So higher order accuracy. All this very advanced answer. But that we're still checking. So I'm not going to read the conclusions out loud. It just repeats what I already said. So thank you very much for your attention. Yeah. Marcos? Or-
Oh, good. Okay, I won't ask about computer functions, but
Yeah.
for the SDs, it smells a little bit like large deviations, right?
Yeah.
I mean, in the sense that
Yeah.
you have a Varadan
Yeah.
principle there, right?
Yeah,
And,
yeah.
and,
I mean, you can look at
which
these
is
as.
sort of
Yeah.
generalized the Laplace principle.
Yeah, you, I mean, there's a large deviations way of looking at it. But that's not how we, I mean, the way we think
Because that
about
gives you the minimi, right? The minimize.
Yeah, I mean, in a certain sense, the you know, the simplest kind of sampler based on kind of large deviation type idea, you would get something like a linear map. So those of you who do Monte Carlo, there's something called a Kramer's sampler for rare events. Not spell with a C, not a K. Yeah. That and so the stuff that I'm saying here with this example, none of this is new. If you look at Peter Glynn's book, you'll see these examples. But and so it's well known that if you do try to take the optimal path as large deviation suggests, in situations where there's more than one possible outcome, you're going to get the wrong thing. And this dynamic thing, we didn't invent this. So this is also very close to Dup's edge transformation for those of you who know these things.
Yeah, and that's related to computer.
Okay. So you're talking about commuter functions for DR, and then
Right, yeah.
What I understand is in computer functions, you need to have two different sets that you're thinking about.
Local minimum, right?
Where you're starting, where you're going.
Right, yeah. You need to-
Come back to where you
In
start
path
first.
space. No, it's in path space.
Yeah. So I don't understand commuter functions well enough to.
Computer function.
This is shooters.
That's the transition path, the Eric's transition path.
Chemist.
There was another question in the. Okay. All right. Okay. Thank you.
Thanks.